Okay, hi. So this lecture is on the chorded winding analysis. And so let's just go back to look at the 12-slot winding analysis design that we talked about in a previous lecture. And in this design we had, so we've got the 12 slots, and it is 2 poles. But we have the distributed winding with the A phase. So the A phase winding is in this example here is in the 12th and the 1st slot, and then the 6th and the 7th slot. And it's 2 layers, okay? And then, so this is the A and the B minus, C plus, and so on, all the way around. So the phase A takes up a total of 4 slots. Now, and we analyzed this in the lecture before last. So now the question is, we have 2 windings in the 1 slot. So now what happens if we were to shift the top? So if we were to shift all the coils in the top slot are moved clockwise by 1 slot. So we move these all round by 1 slot. In that case, we would then get the winding shown here, and so we shifted it clockwise. So now these 2 are A phase, and then we have another A phase, but that is also over the top of the C phase. And similarly on the left side we have a combination of an A and B. So this shifting is called a chorded stator winding. So let's look at what that does to the harmonics. Okay, so hold on there. Okay, so we've shifted that winding that I showed by 1 slot on the top set of windings, and so this winding arrangement is called a chorded winding. And so let's now look at the turns function and winding function for this winding. So we can plot the winding, the turns function, so for phase A. So there's a total of 2 NW windings, and so the first step is NW over 2, and that goes to 30 degrees. Then we come to the second slot has second slot with the phase A winding has an A phase on the top and the bottom. So we have then a jump to 3 NW over 2, and that's at 30 degrees, and then at 60 degrees we again have a jump where it goes to the maximum, which is 2 NW windings, like that. And then nothing happens for the A phase until we get to 180. And then at 180 degrees it comes down again by NW over 2, and then we go to 10 degrees, and then it comes down by N, and then to 40 degrees it comes back down. So that's the turns function. And then the average of the I'll do it over here. The average of the turns function is equal to NW in this case, and so then we can plot the winding function by, as you know, the winding function is equal to the turns function minus the average of the turns function, and so we get minus NW over 2, and then it jumps up to NW over 2 and sorry, no, yeah, so we start here, it's minus NW over 2, and then here it jumps up from minus NW over 2 to NW over 2 because it's jumping up by N over 2, and then we move across again, and then it comes up by NW over 2, so we're at NW, and then we come across to, so this would be 60 degrees, and then this middle here would be 120, and then we come across to 180, and we come back down, then we move across again, and then we come back down, and so that would be, that's 210 degrees, and then this is 240 degrees, like that, and then we go back, then we go down to NW over here. This is now NW minus NW, which is here, like that, there, and so this is the fundamental here. Okay, so now the question is, what are the harmonics for this? So what happens? How does it compare to the other windings that we have looked at? So in order to understand that, we need to find out the Fourier series. Okay. So in order to look at the Fourier series, we don't have to analyze the whole 360. We just have to note that there is some repetition. So let me just redraw part of it. So we can shift the starting point. So we can choose this to be the starting point here. And so in that case, we have a starting point of NW over 2. And then at 30 degrees, which is pi over 6, we go up to NW, and then we move across to 90 degrees, pi over 2, and that's the then it repeats, and so there's, and now it's symmetric, but quarter wave symmetric. So there's quarter wave symmetry. So in quarter wave symmetry, using the same notation we had before, the A component is 0, and then the Bn component, which is associated with the sine terms, is going to be 8 over the period, and then the T over 4, we only have to do a quarter of the waveform because it's quarter wave symmetry, and so this is what we get, where T is in this case 2 over pi, right? Now also for quarter wave symmetry, N is odd. N is only odd. Keep that in mind. So now putting this putting in what we have. So we have Bn is equal to 8 over 2 pi, integrate from 0 to pi over 2, and this is the in A phase, in A theta winding, right? So we have in A theta sine in theta d theta. Now, splitting that up, we have, I'm going to take this out, 4 over pi. So we have from 0 to pi over 6 nw over 2 sine n theta d theta plus the second term, which is pi over 6 to pi over 2 nw sine n theta d theta, like that. Okay. Now evaluating, we have 4 over pi integrating n, we have nw over 2n, and then we have minus cosine n theta evaluated from pi over 6 to 0 plus nw divided by 2 minus cosine n theta evaluated from pi over 2 to pi over 6. Okay. Yeah. And then now substituting in, we have so what I'm going to do is I'm going to take out a 2. So then we have 2. So then we have, so this has got a 2 in it. So I'm going to take that out, and I'll take out the nw. So we have 2 nw divided by n pi, and then substituting in, we have minus cosine n pi over 6, and then they've got 0, minus gives a plus, so we have plus 1, and then the second term is plus 2. There's the plus, the 2 comes about from the need to make it the 4. So we have 2 minus cosine n pi over 2 plus cosine n pi over 6. Okay, now okay. Now let's just rearrange this for one last line. 2 nw over n pi, and so we have 1. So there's a So this is a 2 minus cosine n pi over 2, so let's put that over here. So we have minus 2 cosine n pi over 2, okay? And then we've got a 2 times cosine n pi over 6 and a minus cosine n pi over 6, so that gives us plus cosine n pi over 6, like that. Okay. Now what does, now if we just look at the first term, let's just look at a couple of values. So this cosine n pi over 2, what's that going to be? For n equals 1, that's going to be a, what is it going to be? It's going to be 0, right? And then for n over n 3, it's going to be 0, n 5, it's going to be 0. And so then this whole term becomes 1, right? So you can see that, right? Cosine n pi over 2 is going to be 0, 0, 0, so we get out 1. So this term becomes 1. So then we can further change this into Bn is equal to 2 nw over n pi 1 plus cosine n pi over 6. And now we can use a trig identity to write this as 2 nw n pi times 2 cosine squared n pi over 12. Just using a trig identity there. So finally, putting it all together, our winding function for this one slot shorted winding, now I'm going to write it, I'm going to do it so that it's for all n in this example. So this is for n odd, only odd, but this one here I'm going to write it for all n. So for n equals 1 to infinity, so then we have, so there's a 2 and a 2, that gives us a 4. So we have 4 nw divided by n pi, and that's times cosine squared, and then I'm going to write this as 2n minus 1 pi over 12, like that. Okay, so now let's put in a couple of numbers. So writing it in the same notation as we had before, I can write 4nw over pi, and then we have for n equals 1, 933 sine theta, and then the third harmonic gives us 0.5 divided by 3 sine 3n 3 theta, and then going one step further, plus 0.067 divided by 5 sine 5 theta, and so on. So that's, now if you recall from what we looked at before, that's a marked improvement. The fifth harmonic is now really rather small. So remember, let me just summarize here. So we have n, we have the 6-slot design, we looked at the 12-slot design, and then this is the 12-slot with 1 slot shorting, right? And so for the 6th slot, we've got the odd harmonics, and we had 1 over 3, 1 over 5. Now, and then for the 12, when we went to the 12th slot, So that we got a quite an improvement because it's more sinusoidal. The fundamental went down, so that was now 9.966, and then the third harmonic was 0.707 over 3, and then the fifth is 0.259 over 5. Okay, but then with the 12 slot, 1 slot shorting, since we are distributing the winding more, we do have a lower fundamental, but not by that much. But the third harmonic goes down significantly, and the fifth is really low down. It's almost negligibly small compared to the without the 1 slot shorting. So it really does pay off to short the winding at least by 1 slot. Okay, now next thing to look at is what happens if we were to have 2 slot shorting. How would that change it? So that would mean that there would be for phase A, there would be the winding would be distributed over 4 slots, but it would still be 2 layer. So in that case, how does the winding look, and what is the impact on the harmonics? Okay, so let's also look at this case. So then, in this situation, we can so let me write a little bit here. We can shift. So what happens if we shift the top layer windings by 2 slots? So we have 2 slot shorting now. So in that case, we have to redraw the turns and winding function. So let's do that quickly. So we have the turns function here. Now, so each slot is 30 degrees. So starting at 0, then we go up by NW over 2, then we move 30 degrees. So this was slot 1, then this would be, each 30 degrees is a slot, okay? So then at 30 degrees, we would go, actually let me start this at slot 1 being here, so this is 0 degrees. So this is 0 degrees, and then we go across to 30 degrees, and then we go across to 60 degrees. Then we go, so that's 1, 2, 3, and then we go up again to, this is 90 degrees. And now nothing happens, so this is A phase. Right, nothing happens till we get to 180 degrees, and then we come down, and then we go across to 210 degrees, and we come down again, and we go across to 240 degrees, and then we come down again. There's 1, 2, 3, and then come down again to 270 degrees, like that. Okay, so that's what it will look like, and you can see now that it's going to start looking really sinusoidal. So then the average, this peak here is 2 NW, and this is NW over 2, NW, and 3 NW over 2. Right, now we shift it down by NW, that's the average, and then we get the winding function. So this will be over here before we get to 0. We have so 0 minus NW gives us minus NW, right? So this is minus NW, and then here's NW over 2. So minus NW gives us minus NW over 2. So we're here, and then at 30 degrees we go to 0, and then that doesn't change till 90, where we go up by 30 degrees. So that would now be, that would be now by NW over 2 plus, and then we go up again to NW, and then we go across to here, and then we go back down like that. And that's NW. So wait, am I off there? Comes down, comes down. It's 0. I think I've gone off a little bit here. 90, 180. There. Okay. Now you can now see that we have a real sine wave looking waveform. So once again, we don't have to do the Fourier analysis for the whole winding. We just have to do it for a small section of it. So I'm going to choose it from, I'm going to just choose this point here, this bit here, from here to here, and that's just 90 degrees. So we only have to look at 90 degrees because it's quarter wave symmetric again. So let's now look at the harmonics created by this winding function. So I'm going to go from so in order to do this, now I'm going to take it from this point here. You have to take the middle of this point. So it's a little bit more, didn't quite put all of this on here. So we're going to start this being 0, and then half of 30 is 15. So we go to 15 degrees, and then it jumps up, and then to NW over 2, and then we jump up. So that's from 15 to 15 plus 30 is 45 degrees, and then we jump up to NW at 45, and we go across till 90. And 15 degrees is pi over 12, 45 is pi over 4, and 90 is pi over 2. Okay, so now we need to find the winding function in the Fourier analysis. So so once again, we use Bn is equal to 8 over period 0 to t over 4 in a theta sine n theta d theta, and then n is again odd and t is 2 pi. So we can now put in the terms. So we have Bn is equal to 8 over 2 pi, and then we evaluate from pi over 12 to pi over 4, and so we have nw over 2 sine n theta d theta plus pi over 4 to pi over 2 nw sine n theta d theta, like that. And so that, now evaluating, we get minus 4 over pi nw cosine n theta divided by 2n, and that is evaluated from pi over 4 to pi over 12 plus nw cosine n theta divided by n, and that's evaluated from pi over 2 to pi over 4. And then we can substitute in the limits. And this 2 here will come out and the n comes out. So we have 2 nw divided by n pi, and then the first term is then cosine n pi over 4 minus cosine n pi over 12, okay, plus the second terms, which and now we have to I'm going to put a 2 on the top, because in order to keep the 4 that we need. So then we have 4 cosine 2 times cosine n pi over 2 minus cosine n pi over 4, like that. Okay, this is Bn. So remember, n is odd, so this cosine term will be 0, and there we have a cosine n pi over 4, and then we have a plus 2 times, we have 2 times cosine n pi over 4, so we can simplify down. So we're going to have 2 nw n pi. Now there's a minus out here, remember, so the minus becomes a plus, so we have cosine n pi over 12, and then two of these terms, one of these terms, so we then have plus cosine n pi over 4, like that. And then we can use a trig identity. So we can use cosine A plus cosine B is equal to cosine A plus B over 2 times 2 times Let me put the 2 at the front, times cosine A minus B divided by 2, like that. Okay, so using that trig identity, can reduce this down to Bn 2 NW divided by pi n, and that becomes a 4 cosine 2 n pi over 12 times cosine n pi over 12. So now putting it all together, we have NA theta is equal to 4 NA NW over pi, and summation n equals 1 to infinity 1 over 2n minus 1 cosine pi 2n minus 1 over 6 times cosine 2n minus 1 over 12 pi, and then that's, we're running over here, times, and that's times sine n theta. Okay, so then putting in some of the numbers, we have NA theta is equal to 4 NW over pi. Now the fundamental has actually gone down quite a bit, sine n theta, but there's no third harmonic anymore, and then the fifth is 0.224 over 5 sine 5 theta plus 0.22 over 7 sine 7 theta. So there's no third harmonic, and the fifth is lower. Fifth is lower than the one slot shorting. Okay, so that's what happens if we have the 2 slot shorting. We can reduce the harmonics further, but the cost is a relatively large reduction in the fundamental versus the 1 slot shorting, where the 1 slot shorting didn't have that big an impact on the fundamental. 2 slot shorting did. So we will look at this. We will look at this in terms of distribution factors and pitch factors, and bring it all together in the coming lecture. Okay, thanks.